Good morning. In this lecture, we'll be discussing about the coupling technique of metamaterial structure. So, in previous lecture series, we have seen about DGS structure. So, in this lecture, I'll be discussing about the metamaterial structure. So, how the metamaterial is coupling into the microstrip patch antenna. So, here you can see the 3D metamaterial splitting resonator, where you can see this 3D structure which is printed both on the bottom and the top side of the structure a substrate. So for example, like you can see here is like in bottom side there is an square bracket structure, as well as like in top there is an top of the substrate, there is an air gap between the top of the substrate and dual splitting structure. So here this, while considering this structure with an air gap with an wire, so entire we called as an 3D structure. So this dimensions of splitting resonator is shown here. All these parameters dimensions were used for the calculating the 3D metamaterial structure, and here you can see this how the 3D metamaterials kept in a simulation setup, where we can will assign the boundary condition like E plane at side, and how the H plane is assigning in the other side. So make the as a to send make as a transverse electromagnetic waves. So and here this is an equivalent circuit of this unit cell, and here this is for the bottom of the structure, and here it is of top of the structure. And here you can see this is called as an coupling parameter. This is coupling gap, and here this equivalent circuit of this equivalent parameters is calculated using the frequency and capacitance and inductance parameter. And L3 is the coupling parameters. So this is how we calculate, and here you can see this based on this H plus H is nothing but the height of the substrate plus height of the coupling bag. So this, with this we calculate the what is the inductance and capacitance of the coupling structure. So and here how the design methodology of 3D metamaterial structure has been arrived. So in previously we have seen for the DGS structure also, and here you can see the basic structure of dual splitting resonator. From there I have got to this molded the structure, and here again with this I made with a separate thing, divided the structure, and with this and bias, and then later on I derived with the air gap. And here you can see there is a difference. S parameter is calculated for the all the design structures. So where we have assigned a design frequency of 2.45 for our 3D metamaterial structures. So we have, and there is a reflection coefficient is also very good, and sorry, the transmission parameters is very good, and in here the reflection coefficient is 0 here. So why we are seeing the transmission parameters, like we are making as a transverse waves, where we are passing the electromagnetic fields from the one side, from one port to the other port. And here this you can see unit cell structure, where we have analyzed and tested in the with the VNA, and here you can see the all the reflection parameter is resonating at the same frequency. And here you can see there is an current distribution, and current distribution also there you can see there's a more amount of current in the top of the structure, because we have the coupling bank which it creates a capacitor effect, and by the coupling of top of the structure, the metallic wires, we have the more amount of current is circulating near the top of the structure, whereas in the bottom of the structure. And you can see this one side of the structure will be the unidirectional, like it will be like the current is flowing from the one direction to the other direction. One will be the inward, and other will be the outside of the structure, outward. And here you can see the fabrication prototype, where the top and the bottom of the structure, and fabricated prototype is tested. And yeah, the what we have seen already, that unit cell parameter is of permittive. For metamaterial we see the permittivity and permeability, So this refractive index structure is an mu negative structure, that is permeability structure, where and we have the negative refractive indexes also, where it is resonating frequencies near the I mean, you can see there is a large negative refractive index, and from there I made the structure of 3D metamaterial in the form of an array, like both like 1 cross 2 and 2 cross 1, and then 2 cross 2. For all this, it was resonating at the same resonance frequency of 2.45 gigahertz. So once I got 2 cross 2 for structure, this I made into a large array, and all the effective parameters also satisfied. And here you can see this structure which have been fabricated for the 4 cross 4. So here you can see like 16 cells are there. So already the same output will be like for 2 cross 2, 2 cross, so all the outputs will be the same. So the same similar output we are getting it. And here you can see again it is both we did the measurement, the simulated and measurement, and it was resonating at the same 2.46. And here you can see this current distribution here, and the current distribution is also very very dense at the top of the structures. And here the permittivity and permeability of the refractive index, same as how we have obtained the large refractive index near the resonance frequency. And once we had designed the 3D metamaterial structure, and now what we did is we are going to keep on the top of the structure, like top of the microstrip patch antenna, to enhance the gain of the patch. Like previously we have done for we reduce the cross polarization and we increase the gain, and here we are increasing the gain of the antenna by placing the super substrate. And here for placing the super substrate, this height of the placing the super substrate plays a major role. And here you can see all this parameter has been calculated and derived. And here you can see this a patch antenna with the patch antenna with metamaterial structure, and tested, and all we can see this like measurement, and it is resonating around same 2.45 gigahertz. And here you can see the current distribution is also, and it is getting that we have got the frequency without metamaterial, it was resonating at 3 point gain is at 3.4 dB. Once we place the metamaterial structure, it was resonating at 8.2 dB. It is almost of I mean 5 dB of increment. So far what we have seen is like I'll show you what we did is I'll extend the structure with an array also. So for this array also we have got the same output, where again the dB is also increased, like from 6.9 to 9.5. So this is what we have done. Thanks for watching. In next lecture will be discuss about other coupling structure. Thank you.